All right. I'll go and set up from current slide, though we're not going to use this quite yet. Now, because we had one person absent on Monday, let me just go through. I don't know if you realize or not, we've changed Blackboard from the old Blackboard to what they call, oh man, you know, this electronics really gets to me. Why in the world thing? It knows I want to project. Why does it go and project? Why does it make me plug it in? It's just ridiculous. Don't you think? Yeah. Okay. Gray cells. Okay. Yes, we got recording now. We're recording and we got visuals. So, the Blackboard, have y'all logged into Blackboard? Is it fairly easy to navigate and you see and understand? Are there anything that really were confusing or issues with it? Okay. If you find any, let me know and I'll try to help you. I think it's fairly close to how you did it before. Just looks a little different. You don't have tabs over on the left. Everything is over on the right. Once you get into the course, the syllabus will be there, the research paper, my locator card, the PowerPoints, the YouTube videos, the web assigned class code, everything is there. Fairly easy to see. The PowerPoints will be in a folder, and you'll see PowerPoints. You'll see an up arrow on the far right. If you click on that, then they all open up. Okay. Then it's a down arrow. Then you click on that, and they compress back again. The links you just click on and you go to them. The files, like the syllabus and those kinds of things, I think you have to. It used to be you just clicked on them and they opened. I think what you have to do now, what we have to do now, once you see the file there and it won't open, there's 3 dots, horizontal dots over here. You click on that and it says upload, right? You don't have any other options there, just upload, right? Okay. And if you do that, then your syllabus opens. The research paper instructions open. Remember that fondly, okay? So all that stuff will be there. That's one thing that's less convenient about this. When you're trying to open a file, you have to go to those 3. The links open directly. You don't have to do a thing. You just click on them and they open. The files don't. Okay. Okay, that's it. Now, let's do safety. Now, a few of you have been in my classes before, and you know these drills, but some of you haven't, so let's make sure we get this done. 3 areas of safety. There's nothing we're going to be doing in here that's a safety hazard, okay? But there's still 3 areas of safety you need to always keep in mind, okay? Anyone think of one of them? Fire, exactly, okay? Now let's take worst case scenario. Worst case scenario, the fire starts in this room. Say my computer blows up, okay? It starts, the paper's on fire, maybe even the desk on fire. What do we do? Say again? Run out the door. All right, he's going to run out the door, get to safety, and let the building burn down, and everybody else in here, and he doesn't care, right? All right, yeah, good deal. Oh, he must be a catcher. No, I'm sorry. All right, you still signed something. No, never mind. Okay. No, we will leave, but we don't run, but we will leave, but we do at least 2 things first. What are those 2 things? Probably 3. Say again? Pull a fire alarm. That's an excellent thing to do to let everybody else know the building's on fire. Okay, or at least my desk is. Okay, where is the closest fire alarm? Here we are in this room here. Where's the closest fire alarm? Any ideas? Nowhere that you see here. This is the old part of the building built before fire alarms were coded. There is none anywhere that you see here. But there are some fairly close. Go out the door here, hang a left, go down that little half flight of stairs, go to this corridor here that goes across to financial services. You know what I'm talking about? That's the new part of the building. They do have them there. So you go through that double door and either to the left or to the right. There's fire alarms in both places. Okay? Now I suggest 2 of you go to do that. In case one trips and falls, the other can get there and get it done. Okay? So we do the, okay. So we let other people know. So that's one thing. Okay? What else do we do before we run out of the building? Oh, excellent idea. Okay, now, actually even better than 911. I wish I had the number with me, but I don't. But on most of the doors to this building, coming in or going out somewhere, there used to be on every one of them a sign of 8.5 by 11 piece of paper that had Birmingham campus police number and Bessemer campus police number. Okay, that is not the office where the officer sits in there. That is the mobile that the duty officer has strapped to his or her belt or however they wear them always. Okay? That's the better number to call. So if you can go by an entrance or exit, put it on speed dial on your cell phone. So therefore, if something does happen, you can just get it to it and let them know. Okay? So we've done the fire alarm, and we've done notify either campus police or 911. Okay? Both of those are good. Campus police is better because they can contact 911 like that, but they would be our first responder. We don't want to wait until somebody else gets here, and that's a little bit of time. Okay, one other thing before we leave. Just don't let my desk burn off. Say again? Oh, where's the closest fire extinguisher? Any ideas? This, you didn't have. Right where I'm standing, within 5 feet, right next to the fire. Yeah. Okay, right there is the nearest fire extinguisher within 5 feet of where I'm standing. Really close. And I bet you, at least some of you have always said, wouldn't it be cool to break that fire? You get to do that, if this happens. Okay, once all that is done, now I can handle the fire extinguisher and stuff, but then the rest of you don't run, okay? You proceed slowly, carefully out of the building. Now, where do we go? Here's where we go. Again, here we are right here in this front classroom. Hang a left as you go out, go down the half flight of stairs. The other two, remember, went to the corridor here and went to pull the alarm. You come back and meet everybody else here, or just go out, go down one more flight here, and then head out of the building. Now, here's the aerial view of the building. We're right here underneath the roof right here. And once we go out the doors that are right down here, we head down to that parking lot right down there, from here in Ethel Hall building. A day like today, perfectly fine. A day like yesterday, you might want to get in a shelter somewhere down there because it was raining pretty miserably yesterday about this time. But we stayed together because after I finish the fire extinguishers and that kind of stuff, I leave with the last student. All of you look pretty healthy now, but what if an ankle twist or a knee bend or something? I will be making sure the slowest person, the last person, gets out safely. When I get down there, I'm calling roll again. If we can't account for everyone, someone has to go back into a burning building looking for it, risking life and health and that kind of stuff. Let's not do that. Stay together, and then once we account, I have to report. Everybody's accounted for. Everybody has to report that, and then they'll let us know what to do. So don't say, hey, building's on fire, I'm out of here, driving home, free day. No, don't do that, because otherwise somebody's having to try to trace you down. Okay? So, now, most cases, hopefully it wouldn't be starting here or even in the pantry next door, and we just hear the alarm and we just proceed out. As we said. Okay, any questions on that? There's one safety issue, fire. Another, tornado, or any weather emergency. And by the way, fire, that could do chemical spill, anything happening in the building that we need to get out. Okay? So tornado or weather emergency. Now that will not come from this room. We'll hear the siren in. Believe me, you can hear the siren from here. Okay? So if we hear that go off, you'll probably hear it better than I will. I'm hard of hearing, remember? So, hey, that's a siren. What do we do? What's the procedures in case of weather emergency? Lowest floor, interior. Two good words to remember. Where do we go from here? Out the door here, hang the left, go down this half flight of stairs, hang the immediate left, go down the full flight. This time rather than going out, you go in. The first floor looks a lot like this. A few exceptions, okay? When you come out, right in front of you are the restrooms. Actually, believe it or not, the restrooms are pretty safe places to be. So, the men's room. Okay. The walls are close together and lots of corners. That gives extra safety, extra strength to the building. Okay? Now, here's the other issue. When you're down on the first floor, you're below, back here anyway, below soil level. That whole wall back here that you see represented here is up against the soil. You can't get much stronger than that. That's a good wall to be. Okay? But if you don't want to spend a couple hours in the restroom, which I don't want to do, then if you go down, there's actually a couple more steps that we don't have here going down, and then immediately on your right is the dean's office. Now, she's here this week, so if this were to happen, you go down there and she invites you in, that's another safe place because it's back against that wall, lots of corners, small space, good safe place to be. She may not want you, okay, but that's okay. All right, the next room down that hall is room 160, which is the developmental math room and lab. I don't know if any of you ever went to it, but that's sort of a big room. That back wall, very good. Corners, very good. Any of the walls are pretty safe. Out in the middle, that's not where you want to be. Okay, because that's not your strongest part of the building. Strongest part are your walls, corners even better, that back wall really good. Okay? But it's not a bad place to be. Now, then there's that glass door in the hallway that takes you into the library. You go through that, the first room to your right, as you go through that door, is the computer lab. Now, again, the computer lab is much smaller than the classroom, close walls, lots of corners, and that back wall, strong, okay? So that's not a bad place to be. Right next to that is the reference room, is what I call it. That's where the atlases, the globes, and those kinds of things are. You never check out, but it's pretty good. Again, the back wall is strong, corners are strong. Now, it does have bookcases in there. They're pretty strong-looking bookcases, but if there was some tumbling going on with a tornado, some of those could come off the wall, but not very likely. Okay. Now, there's one problem with every one of those rooms that I've just said. If we really do have a weather emergency, what is likely to happen? We lose power. And if you lose power, every place I talked about, held it's low and interior, perfectly dark. The restroom, black. Okay? Totally dark. So, the place that you might choose to be in, and it's not a bad choice, is the hallway. Okay? The walls are relatively close. No corners to speak of, unfortunately that, but there is emergency lighting. Don't go any further than that reference room, because any further in the library there, you're in exterior. You don't want to be where there's windows. Things come flying through windows, glass comes flying through windows, and you get cut up. Don't do it. Okay. Any questions? Oh, and I'm the last one out, walking with the gimp, whoever the slowest one out is, and I'm taking my roll, and I'm accounting for all attendance. If we can't find you, oh, my dog's outside, I got to go get him. No, you don't. The worst place to be is on the road. Go low and interior. We account for everybody. Then you can mix and mingle until they give us the all clear. Okay? A few years ago, early February, we had math meetings up at Athens State University. And the keynote speaker had just gotten maybe 5 to 10 minutes into his initial speech. He was a real good speaker, And the alarms went off, and they had a tornado sighted and stuff. We were in a hallway with emergency lighting, thank goodness, for about 2 hours, okay? And they said, in the meetings, go home, okay? We did, because there were a risk of more. Okay, so it can happen. Hopefully it won't, but it could. All right, fire or internal problems, weather, external problems. What's the third? Active shooter. A few years ago, I never would have even considered or thought about anything such as this. Things have gotten crazy, okay? Maybe y'all are young enough you think it's been crazy your whole life, and maybe it has, but it used to be this crazy, okay? Now, so far, I can only remember hearing of one community college where they had an active shooter. It doesn't mean it can't happen, but it hasn't happened much. Several major universities have had it, and then all sorts of other venues have had it. So it could happen. Now, again, I'm hard of hearing. You'll probably hear it before I will if there's a rat-a-tat-tat or whatever it is. And you say, hey, that sounds like gunfire. Let me know. What do we do then? Say again?
Take the lights off, right?
All right, very good. First thing I'm going to do is come over here. I want to lock this door so he can't come in. Okay? The trouble is there's no key on the inside. And I can't even open it. There's no button to press to get it to lock. I have to physically go outside, find the key, and lock it from the outside. Press the button to close the door. Okay? I come back in and we'll close the door. You turn off the lights. You're absolutely right on that. But there's another entrance to the room. There's two offices back to back here. And then there's a classroom over there. I don't have a key for that classroom. Okay? Now, would you say it's a good idea to lock this door? It does have a button on the edge, and I can press that button, and it does lock it from the inside, but not from the outside. Actually, this is the inside of the office, but you can't lock yourself in the office. So that's not the one to do. That locks us in and lets him come through. So, there is this door. That has a good strong deadbolt. Trouble is I don't have a key for this. Okay? I don't know if there is a key for that. So that won't do us any good. However, this door is here. Now, right now it's so fast here. That door is closed. I doubt it's locked. Leave it closed, lights off, and just let that be in front. Nobody's in there. So this does have a button. Right? You press that, it locks from the outside, not from the inside. That's the one we press. Okay? We want that to lock from the outside. Then you come back through here, close this door. Oh, that's got glass. He can look in. We don't want him looking in. We want him to think nobody's home. Close this door and close, but don't lock this door. And I think the other thing I've already mentioned it. What's one more thing you've got to remember to do? Say again? Okay. Okay. If it sounds like it's real close to here, we may be the first one. Yeah, we got 911 or Catholic police. But if it's somewhere in the distance, hopefully someone else does that. But just be safe, not a bad idea to do. But as soon as you get that done, what do you do? Say again? Okay. Yeah, we will do that. But what else? You dial 911 or the campus police. What do you do then? Yeah, I've locked the door with that. Says it again, I can't hear well.
Like, move all the discs to the door.
Oh, okay. And not a bad idea. But, probably more important, turn that cell phone off. Because you don't want to connect to you, the other's going to shoot your loss and say, oh, hey, how are you doing? No, we don't want anyone calling in because we want them to think nobody's in here. So that's why we turned off the light. And then, I think what y'all have been hinting at, y'all get back here and we'll join. Okay? Okay? Because guess what? We're out of sight. Hopefully out of mind. He can fire through the window and it'll break. Okay? He can't get you back there. You can probably even fire through that and it might come through. Maybe even the door. I don't know if that's hollow core or not. But guess what? Concrete block, he's going to have a hard time. And if he's there firing a high-powered weapon there, he's going to get more blowback on him than he is on us. So that's the place for all of us is over here. Now, the idea about piling up desks by the door opens outwards, so that's only retards them a little way, but it's still not a bad idea. But we don't want to be making lots of noise. If it's a far way away, we can do that. But otherwise, we're back here, and this is quiet as perfect. Okay? As quiet as we can be until we hear all of it. Now, not to be dramatic about it or anything, but don't be a hero. Okay? Your futures are all ahead of you. Mine's pretty much all back here. If something has to be done, I will do it. Okay? And if I get that weapon away from him, then y'all can kick the fire out of it. Okay? But we hopefully will not have to go that way. But you don't be the hero. If something has to be done, I will. I was in the military. They trained me for this or anything, but let that be me. Okay. And we wait until we know all is clear. Hopefully we won't have to worry about that, but you do need to think about it ahead of time so you don't panic. You know how to react. Any questions? All right, good deal. Any other issues before we get going on actual calculus? I'm so sorry we were late getting started, but after this week, hopefully it'll be normal, somewhat from now on. Okay, now, I think I mentioned to you last time, we're starting with a new book. In previous calculus classes, it was same author, but it was an 11th edition of a slightly different book. This time we're going with Calculus Early Transcendental Functions. That's the new part here. A lot of the rest of this, they're identical because it's the same author, same publisher, same everything. The difference here is basically only for Cal 1. In the old book, Chapter 3, I think it was Chapter 3 was differentiation. May have been 2. No, Chapter 2 was differentiation. But they didn't do anything with early transcendental functions. Then Chapter 4 was application of differentiation, nothing to do with early transcendental functions. Chapter 3. Their Chapter 4 was integration, nothing to do with any early transcendental function. Their Chapter 5 was early transcendental functions, and they went back and redid differentiation and integration and applications in that chapter, which was an awkward way to do it. I found out they had this book which incorporates early transcendental functions in chapter. This one is Chapter 3, differentiation, Chapter 4, application of differentiation, and Chapter 5, integration. There is no separate chapter for them. They're all incorporated in, and you don't have to go back and reinvent the wheel. Okay? So that's why we've gone to this text. Now, in the old book, that's why I was getting my chapters crossed up, the first chapter was called P, and that was preparation for calculus, which was basically a review of pre-calculus, algebra, and trig. In this book, that's Chapter 1, preparation for calculus. We're not going to do that, but it's a good thing to look at, review, take a glance at it, see if there's anything in there you say, ugh, I don't even remember that, or I remember something about it, but I don't remember how you did it. Review that. If you've got any questions on Chapter 1, ask, and we'll go over those on Monday or whenever you run into those questions. So where we're starting today is Chapter 2, limits and their properties. Not quite to calculus yet. We first start off with this concept of limits. Have any of you hit these before? Okay, you may have been exposed to them. So 2.1 is a preview of calculus, which I thought that was what Chapter 1. No, Chapter 1 was preparation for calculus. This is a preview of calculus. Okay? The objectives here are understand what calculus is and how it compares with pre-calculus. We're going to go through this hopefully fairly quickly. I don't do anything very quickly. Understand that the tangent line problem is basic to calculus. Understand that the area problem is also basic to calculus. Now, just for a hint, the tangent line problem basically is differentiation. The area problem is integration. We'll hit that later, but that just has, and those are the two major fields of calculus: differential calculus and integral calculus. Okay. Now, what is calculus? I don't know about you, but when I was a first quarter freshman at Georgia Tech, the maximum my little rural high school had in math was advanced algebra and trig. Okay, that was the senior course. Now the the teacher we had, she happened to know one of my best friends who I later roomed with at Georgia Tech, and she knew he was going there, she knew I was going there, and she knew a few others in the class might be going a little bit higher in math, so she let us read through a pre-calculus book and ask her questions, but we still had to take the test for advanced algebra and trig. So we had to keep up with both. And basically, Paul and I were the only two that followed through with it. The others dropped out. Well, one woman stayed a little bit longer, but I think she finally dropped out too. And they just did the regular course. But I went in with really no concept of what calculus was, even though I'd been exposed to a little pre-calculus. And I went in and opened the book, and the first thing I saw they don't even have it here. Okay. They do, but it's just an altered place. The first thing I saw was something that looked like this. The front inside cover of the book, when you opened the page, had a bunch of things like this. I had no clue what those symbols were. I had no clue what I'd never seen them before in my life. It was enough to be overwhelming. So if you asked me what was calculus, I said someplace I'd rather not be, okay? But, of course, y'all are far better off than I was. You came from good high schools, and you probably had pre-calculus in high school or either here at Lawson State. Georgia Tech didn't have pre-calculus. You jumped right in, okay? So what is calculus? Good, legitimate question. Calculus is the mathematics of change. Now, all math deals with change in some ways, but calculus is the mathematics of instantaneous change. For instance, calculus is mathematics of velocities, accelerations, tangent lines, slopes, areas, volumes, arc lengths, centroids, curvature. Boy, this is just as bad as calculus, isn't it? What in the world is a centroid? I don't know. Okay. And a variety of other concepts that have enabled scientists, engineers, economists, all sorts of people, biology, all sorts of people to model real-life situations they could not before. Now, I'm sure they'll go into a little bit of this, but from my understanding, there was a guy, I believe it was Kepler, Johannes Kepler, German, I believe, scientist, who amazingly finally figured out formulas and equations of why the planets move like they did. Okay? Before him, there were all sorts of theories. None of them worked well. He somehow figured it out that planets are in elliptical orbits, not circular orbits. Okay? The sun was one of the foci of the ellipse, but there was another one. Okay? It wasn't important, but it was. Okay? He came up with these formulas. He came up with this explanation, and it worked like a charm. Trouble is, he had no clue of why. Why do these things work? Why is an elliptical orbit not a circular orbit? Why does the area in a given time the same whether you're moving fast or moving slow? Why are these things true? Relationship between the cubes and the cube roots and the why is this true? He found out they were true. There's 3 laws of planetary motion, but he didn't know why. And I think he contacted this guy over in England named Isaac Newton. He said, "Can you come up with any? He's a great physicist, great mathematician. Can you come up with any justification for why these work?" And Newton started working on and he found out the math of his day didn't work. You couldn't do it with that. So he came up with the concept of instantaneous changes. And that's where calculus came from. Okay? Areas of curves, okay? That was in there. The instantaneous velocities, accelerations, all those were in there. He had developed the math to explain the physics. That's the beginning of calculus. Now, another guy in Germany also, Gottfried Leibniz, was working on the same thing too, but there was a big dispute over whether Leibniz stole some of Newton's work or not, or whatever. But anyway, those were happening. Although pre-calculus mathematics deals with velocities, with accelerations, with tangent lines, with slopes, with, and so on, there's a fundamental difference between pre-calculus mathematics and actual calculus. Pre-calculus mathematics is more static. You talk about average velocity, average acceleration, slope of a single static tangent line. Okay? That type of thing. Whereas calculus, instantaneous. What is happening at any point on that curve. Can't do that with pre-calculus. Here's some examples. An object traveling at a constant velocity can be analyzed with pre-calculus mathematics. Yeah, if you have constant velocity, your acceleration is 0, everything works fine. To analyze the velocity of an accelerating object, whoa, the velocity is always changing. If it's accelerating, the velocity is never the same between 1 second and the next second. 1/10 of a second, the next 10th of a second is changing. If it's accelerating and changing, that's calculus. The slope of a line can be analyzed with pre-calculus, but to analyze the slope of a curve, not a line, yeah, we can figure that out, rise over run, right? But a curve that's always changing, you can't. You need calculus. Okay? That's what Kepler had run into. The curvature of a circle is constant and can be analyzed with pre-calculus mathematics. A perfect circle, fine. To analyze the variable curvature of a general curve, like an ellipse, oops, you need calculus. Okay? And since they were elliptical orbits, pre-calculus didn't work. The area of the rectangle, yeah, length times width, I can calculate that. Pre-calculus math is fine. But the area under a general curve, that's a different story. The area in an ellipse, different story. Okay? You need calculus. Okay? Each of those situations involves the same general strategy. The reformulation of pre-calculus mathematics through, unfortunately, the use of a limit process. And I'll confide with you. My least favorite part about calculus is the part about limits. Okay? It's just sort of a pain in the neck or some other body part. Okay? It's just issue. Okay? But it's necessary. So one way to answer the question, what is calculus, is to say calculus is a limit machine that involves 3 stages. First stage is pre-calculus mathematics, which you have had, such as the slope of a line or the area of a rectangle. Oh yeah, we can figure those. The second stage of the limit is the limit process itself. The third stage is the new calculus formulation, such as a derivative or an integral. Okay? And you'll see, even those weird-looking symbols I was telling you about that scared the daylights out of me when I opened my calculus book, they really come from pre-calculus algebra. Just a little bit of a twist or spin on it. So we'll do pre-calculus mathematics, take it through the limit process, and get to calculus. Okay, this is a lot of blah, blah, blah here, isn't it? Okay, here's some of the familiar pre-calculus concepts coupled with the calculus counterpoint. Okay? Without calculus, if you have a function here, y is equal to f of x, that's what pre-calculus algebra was. The algebra of functions, okay? You can find out, given a value x, c, x equals c, you can plug c into that function and find out what the y value was. Okay? Find the value of f of x when x equals c. Plug it in, okay? Now, with differential calculus, this is not integral, but differential calculus, what is the value as x is approaching c, even though it may not be defined at c itself? Can't do that with this. You can with the limit process. That's differential calculus. Slope of the line, yeah, we can do that. Rise over run. We know how to do that. Okay? Slope of a curve, however, is there is no straight line in this. Parts of that look like they could be close to straight, and parts are very different from straight. Well, now, what was this? Delta y over delta x, change of y over change of x, rise over run. Now we take it to a dy over dx, where d is now an infinitesimally small segment. In other words, your dx is approaching 0. What's the problem if delta x was 0? Rise over run, you can't divide by 0. You still can't, but you can do a limit process, and that gives you the derivative. Okay? Now, secant line to a curve. Here's a curve. Pick 2 points on the curve. What's the slope of that secant line? Well, again, it's rise over run. You can do that. You can't tell the slope of the tangent that's up here, but you can do the secant. But if you want the slope at an individual point, here your delta x is finite, right? Delta y is also finite. Delta x is finite. Rise over run. Here, you have a rise. You can tell there's a rise, but now the run is going to 0. So again, it's a limit process where your delta x is approaching 0. Now, in pre-calculus algebra, you can do the average rate of change between 2 points. And you did that. In fact, you called it a couple different things. Remember when you talked about, goodness, what is that terminology they use? One of them was average rate of change, but the one before that was difference quotient. A difference quotient. The quotient rise over run of the difference between y and difference of x, that's the slope, a difference quotient. When you get to calculus, though, it's rise over run, where the run is now going to 0. So, same thing with average rate of change. What was your, say, your speed here? What's your speed here? Average rate of change of speed, that's your acceleration. But, what if you're saying, what is the acceleration at that point when t is equal to c? Now your time interval is 0. That needs limit process with calculus. All right, here's some more. Boy, this is pretty old, don't we? Curvature of a circle. Oh yeah, we got formulas for that. You might not know where they came from, but we got formulas for it. But what is the curvature of a curve? In other words, what circle at this point matches the curve best? Okay? You've got to have calculus with that. That's the limit process. You can do this by itself. Because you see, the curvature here, that's a pretty reasonably sized circle. You get up here, it's going to be a bigger circle. Get down here, it's going to be a smaller circle. Up here, it'll be a circle on the inside of this. So they're always changing. This is constant. Okay, how about this one? The height of a curve when x equals c. If you know what f of x is, you can plug in c, you got it. But what if you wanted to know the maximum height on this interval? Well, you can look at the curve and say, I think it's about there. That's all you can do. Calculus tells you exactly where it is. What if we have a sphere here? We know the tangent plane. You probably don't, but you can do it with pre-calculus algebra, the tangent plane of that sphere. What if you just have a surface that's not a perfect sphere? Then how do you get the tangent plane at any point on that surface? Calculus. Okay? If you're doing motion along a straight line, yeah, you can do that, okay, without calculus. If you're moving motion along a curve where it's constantly changing speed, direction, and other things, you've got to have calculus for that. Cannot do it with pre-calculus. More, okay? Now, area of a rectangle. length times width. We know that. That's easy. If that was all there was, let's keep dancing. Okay. But what if we have area under a curve between this point and that point? Whoa. That almost looks like a trapezoid, which you could approximate the area, but you wouldn't know the exact area. Okay? Or, what if you had a constant force pushing on an object, moving an object? Yeah, we know the work. Work is force times displacement. Pretty easy. What if this was a variable force, like a spring, or anything such as that? You can't do that without integral calculus. Center of a rectangle. Yeah, you can figure that. You may not know how to, but it can be figured. But what if you have a curved region here? Let's call this a name for that too, and I've gone blank on that too. There's just a curved region under here. What's the centroid of that? You know what the center is. What's the centroid? Well, it depends on a lot of things. You got to have calculus. Length of the line segment? Yeah, we can figure that. There's a formula for derivative change of x squared plus the change of y squared. We can do that. Even three-dimensional line you can do it. But what is the length of the curve? Blue. But that's harder to do. Integral calculus will give it to you. That's called length of an arc. All right, goodness. More of them. The surface area of a cylinder. We can figure that out. If that's a cylinder, what you can imagine there's a surface area of that. Now, if you're counting the ends, that's a circle, or whatever shape it happens to be, you can calculate that. But the cylinder, if you cut it right down here, flatten it out, that makes a rectangle. You can come up with the area. It's doable. You can do the circumference of the circle, that would be the width, and the length would be the length of it. Okay? But what if you have some weird looking shape like this? How do you do the surface area of that? With integral calculus, that's how you do it. We won't get to all this in this term, but this is just show it. What if you have a mass of a solid, or you're wanting to calculate this, if that solid has a constant density? Yeah. Well, you can do the volume of that solid as well, especially if it's a regular solid like this. Length times width times height. Density is mass per unit volume. Multiply those two together, you get the mass. But what if this is variable density? It's real dense over here, but not as dense over here. What if you have variable density? No way you can get the mass without integral calculus. Okay, let's go back to the volume of that rectangular solid. You can do that. But what if this is a weird looking thing like that? Now this is another area of calculus we're just going to touch on here. The sum of a finite number of terms. If you have just a fixed number of terms, no matter how many there are, you can add them all up and get the sum. But what if you have an infinite number of terms? Whoa, you can't add all those up because it's an infinite number. But calculus enables you to determine, number one, if there is a sum or not. There may not be. The calculus tells you that. And if there is a sum, then it tells you how to calculate. Can't do it here. You can with finite sum, but you can't do it infinite unless you have calculus. Whew. All right. So now we move to the tangent line problem. Now, periodically in the book, you'll have little features about certain people. On page 69 in your text, there is a little blurb on Grace Chisholm Young. Okay? Lived from 1868, by the way, from England, so it wasn't here in the U.S., but that was, 1868 was just after the war between the states, and she lived almost up until World War II, so she lived through wars. Say again? Yeah, Grace Chisholm Young. She received a degree in mathematics from Girton College in Cambridge, England, which was fairly unusual at that time. A lot of times women weren't allowed to go to school. She was just at the time when they were allowed, but very seldom did they go into mathematics. She was very bright. Her early work, she was incredibly bright. She came up with a lot of great ideas, but no one was going to listen to them because she was a woman. So she published her work under her husband's name. She had been Grace Chisholm. She married William Young, so he got the credit for it, okay? He knew it was hers, but they couldn't publish under her name because no one would pay attention to it. She published work on the foundation of calculus that won her the Gamble Prize from Girton College. Okay. Now, that has nothing too much to do with what we're doing, but why I mentioned that, remember your research paper? If something like this intrigues you, this can't be your source, this can be an idea for your paper. You need to get your source from outside the book, okay? So you can't just type up this and say that's my paper. Won't work. But anyway, let's go on. The tangent line problem. The notion of a limit is fundamental to the study of calculus. Every new thing we do in calculus, we're going to be dealing with limits. The following brief descriptions of two classic problems in calculus, first, the tangent line problem, and second, the area problem, should give you some idea of the way limits are used in calculus. And they're pretty good things. They certainly are very useful. In the tangent line problem, what you're given is a function. Y is equal to some function of x. Maybe a very complicated function, maybe a very simple function. It could be a polynomial function. It could be something else, okay? But you know what the function is, okay? And you know one point on that graph of that function. We'll call that point P. Pretty incredibly original name, right? Point P, okay? Now, if you want to know how that function is changing at that point, the best indicator is the slope of that tangent line. And here's the problem with the slope of the tangent line. The slope of any line, you need 2 points. Here you have 1 point. You don't know how it's changing vertically or how it's changing horizontally because it's not changing. At that point, it's fixed, okay? The delta y over delta x would be 0 over 0, which in the old days, you say, you cannot divide by 0, okay? And indeed, that's still true. You can't divide by 0. However, I use this more than the book does. So this is how I learned it and it made more sense to me. If you had 7 divided by 0, undefined, you cannot do it, ever. 0 divided by 0, though, is what we call indeterminate. You may or may not be able to do it. You can't do it with regular math, but you can do it with numbers. 7 divided by 0, you can never do, ever. Or negative 13 divided by 0. Anything divided by 0 other than 0, you cannot ever do. But using a limit, you may be able to do what they call an indeterminate form, 0 divided by 0. And that's what you got here. The slope of that line is change of y over change of x, but these are both 0. So if there is a limit, that will give you 10. So we've got to figure out if there is a limit. We know there is. Look at that. That does have a tangent line. It has a slope, but you can't figure that out unless you know calculus. Except for cases involving a vertical tangent line, that's a real big problem, okay? The problem of finding a tangent line at a point P is equivalent to finding the slope of the tangent line at point P. Because if you know the slope of the tangent line, you can figure the tangent line. So guess what? If you know the slope and a point, you can use the point-slope formula to give you the equation for the tangent line. You can approximate the slope by using a line through the point of tangency and a second point close by on the curve, but that still won't give you the tangent. It helps you get an idea of the range maybe. So if you choose this point here, where x equals c and your y is f of c, because this is the function y is equal to f of x, and then you let x increase a little bit from c plus delta x, that's a really big delta x, then over here you're at c plus delta x, and up here you can do f of c plus delta x. So This point here is c plus delta x, comma, alpha c of delta, alpha c plus delta x. Over here is c and alpha c. So the slope of the secant line is alpha of x plus delta x minus c over alpha c. I'm sorry, I said that wrong. Alpha of x plus delta x minus alpha c divided by c plus delta x minus c. Well, that just gives you delta x here. Okay? So alpha of c plus delta x minus alpha c, that's your rise. Your run is your delta x. So you can get the secant line, the slope of the secant line, by just doing rise over run, just like we did before. And that's what we called difference quotient. The difference of this divided by the difference of that. That's what we call average rate of change. This is the change of y over change of x. That gives you your average rate of change. It's not a tangent line, but it's a slope of the secant line. Okay? Now, anyone think of a way you can approach a tangent line? Let's use smaller and smaller delta x's. Here the delta x is there. That gave you that slope. What if you move the delta x to here? Now your slope is there, or there, or there, or there. And as the delta x approaches 0, you're approaching the slope of the tangent line. Exactly what we do. But you can't divide by 0. But it does form a limit. An indeterminate form, and your limit can tell you what that slope is. Okay. So if P, point P, which is C, f of C, is the point of tangency, and Q is that other point over there, C plus delta x is the x value, and f of C plus delta x is the y value, that's the second point on the graph, then the slope of the secant line is rise over run, this y minus that y over this x minus that x. Okay? This, c minus c goes to 0. That just gives you the change of f over delta x. Okay? And for any delta x, any finite delta x, you can get the slope of that secant line. And m sub SEC means the secant line. But what we don't know how to do yet is what if that delta x is approaching 0. Well, if the delta x is approaching 0, then this is alpha c minus alpha c. That's approaching 0, right? Well, then you have a 0 over 0 indeterminate form. If that has a limit, you have a slope. If it doesn't, you don't. Vertical line, it wouldn't have a slope. Because a vertical line, whatever change of f you have, the change of x is 0. Okay? 7 over 0 minus 3 over 0, whatever over 0, can't do it. That's undefined. But as long as that's not a vertical line, then you can come up with a slope. And that's what we'll be doing. So as the point Q gets closer and closer to P, the slopes of the secant lines are approaching the slope of the tangent line. So here's that first Q. Now you let Q move down from here. There's the second slope, then the third slope, then the next slope, and it's getting closer and closer to the slope of the tangent line. Okay? That's your limiting process. You get closer and closer to some value to see if you can determine what it is when your delta x is 0. The limit of the slopes of the secant lines. That's the slope of the tangent line. Now, we're not telling you how to do it. This is just this blah, blah, blah introductory stuff. Just to get your mind thinking on it. Whatever. I don't like the way they do this, but anyway, they do it. The area problem. Second classic problem in calculus is finding the area of a plane region bounded by graphs of functions. That problem can also be solved with the limit process. In this case, the limit process is applied to an area of a rectangle, which we know, to find the area of a general region, which we don't know. So here's what we do. Here's a simple example. Consider the region bounded by the graph of this function, y is equal to f of x. Now, I have no clue what that function might be. maybe a polynomial function, maybe some other function. Whatever it is, we know the function, okay? It's bounded by this function, the x-axis down here, and the vertical lines x equal a to x equal b. Does that increase? We want to know its area. I don't have a formula for that, okay? Can't do it with pre-calculus algebra. So what do we do? Now, before they show you, I'm going to show you. Let's split this region here. Why am I not getting my pen? There we go. We finally got it. There we go. Why is the system being so bizarre? Okay, there we go. I like to use black. Okay? Let's split this x-axis into subintervals. Okay? And the first of these, we'll call this a delta x, change of x. And this will be delta x1, delta x2, and so forth. Then we do this and make a little rectangle here. Take the midpoint there or some point and make a rectangle. Well, the height is the value right there, f of that value there. The width is delta x. The next little rectangle, height would be this value here, and the width is delta x. The next little rectangle will be this height here times delta x. And we keep doing that. So now we have a whole bunch of rectangles that we can calculate. They're not going to be exactly that area, but what we do, let the delta x get closer and closer to 0. Now those rectangles are closer and closer to the exact area under the curve. Again, a limit process. The delta x's go to dx, infinitesimally small x's. But you have to add them all up. Adding is a summation, and if you have a whole bunch of them, that becomes almost looks like a long S, meaning sum. Okay? So that's what they show here. Let's first take 4 rectangles. Now we're going to use the left-hand endpoint too, so we don't do the midpoint. So here's your first rectangle. That undershoots this by that pink amount. That's pretty bad undershoot. The next one will go from here, with undershoots here, but overshoots just a little bit there, still a pretty serious undershoot. The next one will take this one here, that overshoots by that amount, and then the next one will go from here, and that undershoots again. It's going to be an approximation, not going to be a very good approximation, but it'll be better. I mean, it'll be an approximation. But now let's take, rather than 4 increments, do 1, 2, 3, 4, 5, 6, 7, 8. In other words, you take halfway in here, halfway here, halfway here, halfway there. Now this undershoots a little bit, less than this. This undershoots a little bit. This undershoots just ever so slightly. This overshoots a little bit, overshoots a little bit, undershoots a little bit, undershoots a little bit, undershoots. But guess what? A better approximation. This blue here is closer to the original pink. Okay? Not exact, but closer. What do? Keep taking smaller and smaller delta x's. Now, the next one, we have a very small undershoot, very small. They get less and less error between the two. That's a limiting process. We'll do that, chapter 4, I believe it is. As you increase the number of rectangles, the approximation tends to become better and better because the amount of area missed by the rectangles decreases. Your goal is to determine the limit of the sum of those rectangles as the number of rectangles increases without bound. Oh, guess what? Now we're adding an infinite number of rectangles because they increase without bound. But calculus will do it for you in a really interesting and unique way. How in the world Isaac Newton came up with this, I don't know. But oh, goodness gracious. That's it, thank goodness, for 2.1. Here's a little thing called a historical note. You can read those if you'd like. There's a couple of things called explorations. You can look at those. There's homework exercises here. But before I get into that, notice there wasn't a single exercise in that whole section. Okay? Later we will have exercises in every section. Lots of exercises in every section. Or examples, I'm sorry, I'm using the wrong word. After every example, you will see larsoncalculus.com. That is an absolutely free website. You don't have to purchase the book. You don't have to have been in a class. You don't. Anyone, your grandmother, could go to larsoncalculus.com and get on the website. Most of the examples that are given in the text, at the end of them, they'll also give a checkpoint. That's what they call a checkpoint. That's very similar to that one. All those checkpoints are located at larsoncalculus.com. larsoncalculus.com. There's also pre-calculus for the other book. Okay. Now, on there are interactive examples. There's videos. There's three-dimensional graphs. I don't draw three-dimensional graphs, so use them there. Videos with Bruce Edwards, who's one of the authors, and editable spreadsheets. That's not edible, it's editable. Okay, you can edit them. You don't need them. Okay, spreadsheets. Now, the reason I mentioned that first, that's the first one. Then these homework exercises here. There's some under concept check. You can read through those, and that's fine. But usually I start here. Now, the odd number exercises, here's 3, 5, 7, 9, and 11. Okay. There's only those. All those odd number exercises, number 1, have answers in the back. But number 2, if you do this, you come up with an answer, you look in the back, it's not right, you can't figure out how to get it, then go to calcchat.com. There's another absolutely free website, no code required, anyone can go there, you don't have to have a code, and at calcchat.com you'll find tutorial help and worked out solutions for all the odd number exercises. Guess what? Your assignments are always going to be the odd number exercises. So you can use the back of the book, you can use calcchat.com. Okay, and they talk about calcchat back here too. Now, certain of these exercises are occasionally in red. See, number 3 is in red, 5, all the rest of them are in black. The ones that are in red, now if you have a cell phone, which most of you do, and it has a QR code reader, is that what it's called? You can just bing on that, read it, it will open you right up to calcview.com. Another absolutely free website. Anyone can access this. Of course, you need the book to read the QR codes, but you can go to calcview.com, and at those, you have video solutions, not just worked out solutions, video solutions to selected exercises. There's not an author I know of that provides so much absolutely free help as this one does. So you can do any of the odds, 3 through 11, they're all at CalcChat, 3's at CalcView. So let's move on to let's move on to yuck. That wasn't supposed to happen. Well, everything out of there. Did that come back yet? Okay. Supposed to shut this down. We're not supposed to have lost video. I've got my video back, but it's not here yet. Okay. Let's go to 2.2. By the way, it's what, 11:23, we go to 11:40. So I don't have my watch, my battery died, so y'all don't let me go too late, okay? Christian will let me go forever, so you have to override him. Okay, let's see if this will ever open. And if I can get my video back. The video back. This makes no sense. I didn't do anything. Not back yet. Well, it did. Something changed. Does anything happen? What's that? I can't hear. This? Unplug this? Okay, let me try that. Okay. Otherwise, I think you have to shut down the computer and start back over again. I'm loath to, hey, look at you! All right. And there goes my flash drive. I told you it was a sorry one. So I don't like messing with it. Okay. Yuck. Too many moving parts. All right. I think we're back here again. Let's go from current slide. I don't want to do that. Okay. All right. We're still in Chapter 2, limits and their properties. A lot of blah, blah, blah so far. 2.2 is finding limits graphically and numerically. Frankly, I like numerically best. Easier to do. Graphically, kind of a pain in the neck, but it's doable. So, what our objectives here are to evaluate or estimate a limit using a numerical or graphical approach. We'll learn different ways that a limit can fail to exist, and we'll study and use a formal definition of a limit, which is really a lot of fun. Okay? I don't like tuxes, and those are formal. No, never mind. Okay. So, here's the introduction to limits. Okay? First subtopic here. What if you were doing this? You're trying to sketch the graph of this function, really a hairy-looking function here. F of x is equal to x cubed minus 1 over x minus 1. We're going to graph that, sketch it, for values other than x equal 1. Why wouldn't we want to do x equal 1? You can't divide by 0, can you? Now, we were saying that's not defined. But what happens if you plug in x equal 1 up here? You get 0 there too. 0 over 0 is one of those indeterminate forms. It may not have a limit, or it may. If that would have come up, if you plugged in a 1 here that came up with a 17/3 divided by 0, you never will get an answer to that. 0 over 0, you may or may not get an answer. Okay? So let's just throw out x equal 1, we won't consider that, and use all of our other techniques. You can use standard curve sketching techniques, but at x equal 1, it's not clear what to expect because you have a 0 over 0 there. Everything else you can plug in any value you want to. 0 would be, if you plug in x equals 0, you get minus 1 over minus 1, that's 1. You plug in 2, you get 8 minus 1 is 7 over 1. That would be 7. Negative 1 would be negative 2 over negative 2. That would be a 1. Okay. You can plug in any other value except x equal 1. You can't plug that in. So you can plot all those points and see what to expect. Now, I really want to do this the easy way. Would you mind if I cheat a little bit and do it the easy way? Okay. Because later we'll call it a technique. Right now it's cheating. Okay, but later we'll call it a technique. The question here is, well, get my pen. There we go. Can you factor that numerator? Oh, yes. How? Oh, boy, do I have to remember that? That was back in... no, yes, you do. How does that factor? x minus 1 times x squared plus x plus 1. Y'all didn't remember that, did you? You did. Excellent, excellent. Divided by x minus 1, and guess what happens? There goes your problem child right there, out the window. Now, you can plot that. That's a quadratic function. You can plot it. Give me an x, plot it. You can even put x equal 1 in here, and that would be 1 plus 1 plus 1 would be 3. Okay? But you can't put x equal 1 in here. So therefore, technically, x equal 1 is still undefined, even though you can plug it in there. But guess what? That's the limit. As x approaches 1, the answer is 3. Okay? I cheated. Okay? But this is an analytical way to do it. They want us to just do it graphically and numerically, which is really a pain. Analytically, much better to do. Okay? Much easier to do, in my book, anyway. All right. So how do they want us to do it? To get an idea of the behavior of the graph of f as x approaches 1, we start picking values of x near 1, but not equal 1. So here's what they did. They started off with 0.75. Plug that into that rational expression, you get 2.313. Get closer to 1, like 0.9, you get 2.710. You can plug these in your calculators or whatever. Do closer even, 0.99, you get 2.970. Get even closer, 0.999, 2.997. Okay? Well, you can keep getting closer and closer, but it looks like this may be getting close to 3. What did we have before? 1 plus 1 plus 1, 3. But let's approach it from the right-hand side. 1.25, plug that into the thing, you get 3.813. Put 1.1, getting closer to 1, but not getting to 1, 3.310. 1.01 is 3.030. 3.001 would be 3.003. Guess what? That looks like it's approaching 3 also. So, numerically, it looks like it's approaching x equals 3. That's a lot of calculations. I mean, I didn't do the calculation, I just read off the board. You can punch it in on your calculator and in the neck, but you can do it. It approaches 3 from the left, approaches 3 from the right, stand up, sit down, fuck no. You figure the limit must be 3. Okay? Now, the graph of the f is a parabola. Now, how would you have known that? Well, we figured it out. Okay? When you factor out common factors, it became a parabola. But you still can't let x equal 1, so therefore that parabola has a hole at the point 1, 3. Okay? You know that if you approach x equal 1, that's getting close to 3 this way, getting close to 3 that way, but you can't put a value in there from this because you can't divide those zeros. So you leave that being a hole. Okay? And it's approaching 3 as x is approaching 1 from the left and the right. All these other values, who cares? Okay? So x equal 1. That's a hole in the graph. Okay? Although x cannot legally equal 1, you can move arbitrarily close to 1, and you see that it gets closer and closer to 3. So using the limit notation, that's the first time we've seen this. LIM stands for limit. The limit as x approaches 1 of this f of x, you could actually write that in if you wanted to, x cubed minus 1 over x minus 1 is equal to 3. Because you did it numerically, on that table we just had, you can look at it graphically and see the limit as x approaches 1 of that function f, that one right over there, is 3. The value is not 3. There's a hole there. There's no value, but the limit is 3. Okay? So, this is how you read it. The limit of f of x as x approaches 1 is 3. I like to say the limit is x approaches 1 of f of x is 3. However you want to say it. Any questions on that? So I've already given you one way to do it analytically. See if you can factor out a common factor, and if that common factor is the thing that was causing you problems, then you're ahead of the game. This discussion leads to an informal definition of a limit. Okay? In my mind, I ought to go on and hit you with the formal one, but we'll do this. If f of x becomes arbitrarily close to a single number L as x approaches c from either side, then the limit of f of x as x approaches c is that number L. Okay? So we write it just this way. The limit as x approaches c of f of x is L. Now, that's if it exists. Now here's what they say, the informal definition. Why did it say informal? Because of weasel words. That's why. Arbitrarily close. What does that mean? As x approaches c, that's a little more obvious, then the limit is that as x approaches c is value L. That is the key weasel word here. What do we mean by arbitrarily close? Okay? And that's where our formal definition will come into play, and that's even worse, but we'll get there later. I don't want you looking forward to something negative. So here's your example 1. Evaluate the function f of x equal x divided by the square root of x plus 1 minus 1 at several values near 0, and use the results to estimate the limit. Now, why do you reckon they said near 0? What happens if x is equal to 0? Well, certainly we know what's happening in the numerator. Well, that's approaching 0. Well, that's fine. Numerators can be 0 anytime they want to. Okay? But what happens if x is approaching 0 at the denominator? This would be the square root of 1 is 1 minus 1 is 0. So I've just given you another little hint. Maybe this was cheating too. Here's what we do. If you have a limit, try plugging that in, just to see what happens. If that came up 0 over 17, 0 is your answer. That's the limit. If it came up 0 over negative 45 pi, guess what? 0 is your answer. But if it comes up 0 over 0, you don't know the answer. That's your indeterminate point. Now, if it came up 17 over 0, that's never going to have a limit. But if it comes up 0 over 0, indeterminate. So the first thing you do, plug it in, plug it in. This gave us 0 over 0, which we don't know. It may or may not have a limit. Now, what do they want you to do? Since the x equals 0, that's the unknown quantity, that's your indeterminate form there. They want you to pick some points near 0. If I were doing this, I would say 0.1, 0.01, 0.001. You're approaching 0 from the left-hand side, right-hand side. And then I might do a negative 0.1, negative 0.01, negative 0.001, approach it from that side, and do those lengthy calculations, punching away on your calculator, see what you get. Y'all want to find the easier way? Okay. Here's another hint. Now, I shouldn't be doing this yet, but to me, I don't see any reason not to. All right. Anytime you have radical forms, if you really had a number here, okay, give me an x other than 0. 2, okay? What if x is equal to 2? The numerator is 2. The denominator is 2 plus 1 is 3. The square root of 3 minus 1. Now, if I was doing that by hand, I would want to spit. I would not be a happy camper, because square root of 3 is an irrational number. And you have all this decimal that goes forever, and you're subtracting 1 for that, which you can do, but it's still an irrational number. Dividing by irrational numbers is a pain in the neck, or the body part, okay? Well, what did we do back in algebra when we had radicals in the denominator? Yes, excellent. You multiply by the conjugate. So let's do the same thing now. Okay? Okay? What is the conjugate of that denominator? Square root of x plus 1 plus 1. This one was minus 1, this one's plus 1. You don't change the sign inside, you change the sign outside. Okay, that's the conjugate. But if you do that, you have to do it here too. The square root of x plus 1 plus 1. Now, why do you want it to do that? Yes, this is 1, isn't it? And when can you multiply by 1? Anytime you want to. It doesn't change the value at all. Okay? You have to multiply this by 1, this by this because it's its conjugate. So you can't just do that. But if you multiply the numerator by that same value, you have to change the value of the whole expression. Now, it does look messier, doesn't it? But let's see what happens. X times this, numerator gets messy now. X onto the square root of x plus 1 plus x. Okay? All right, big deal. What happens to that denominator? Say again? Okay, not quite, but some things cancel. You FOIL it, right? First times first. Well, that's two radicals multiplied together. That just, and same thing underneath, that would just give you x plus 1, right? Square root of x plus 1 times square root of x plus 1 is just x plus 1, right? Okay. Now let's do the outer, okay? And that would be the square root of x plus 1 times 1. I can do that. And then you do the inner, and that's minus 1 times the square root of x plus 1. Guess what that gives you? Square root of x plus 1 minus square root of x plus 1? 0. That's why we multiply by the conjugate. A plus b times a minus b is a squared minus b squared. You lose those cross terms. That goes to 0. And then what's the last term? Minus 1 times plus 1 is? Minus 1 times plus 1? Minus 1, isn't it? Okay, help me out here, folks. Say again? The minus 1, the last term here, times the last term here, that gives you minus 1. Well, plus 1 minus 1, that goes to 0. This is getting interesting. So what do we have up here? We have x times the square root of x plus 1. Well, why did I do that? Silly me. Okay. I shouldn't have multiplied through. I should have kept it just like it was. X times the square root of x plus 1 plus 1. That's what I multiply by. I should have left it just like that. And your denominator now becomes x. And guess what we can do? Divide out our problem child. X equals 0. Get rid of that. Now, let the limit as x approaches 0 of this, which is the square root of x plus 1 plus 1. And this time you plug it in, and x equals 0. That becomes square root of 1 is 1 plus 1 is 2. Didn't know you'd be doing such high-level math today, did you? 1 plus 1 is 2. Okay, y'all got that one? Okay, good. So the limit is 2. Now, you might say that might be longer than plugging in all those values. I don't think so. Once you get the hang of it, that's easy. Okay? So, it does have a limit, and that limit is 2. If you drew the graph of that thing, you'd have to put a hole at x equals 0, because it can't equal that, but that hole would be at the point y is equal to 2. Okay? Now, are we almost out of time? Okay. Let's just go through and show you the answer. Let me see. Yeah. They did it like I said. They started with minus 0.01, minus 0.001, minus 0.0001, plugging it in and calculating. They don't show the function here, but that's a pain in the neck. But you see you are getting closer to 2 this way. don't know what it is at 0 because it's not defined there. And then at 0.01, 0.001, 0.0001, closer and closer to 0. So this goes 2.004990, 2.0050, 2.00005. That's getting closer to 0 here and there. So the limit does appear to be 2. And we just worked it out and saw it definitely is 2. Okay? So this is doing it numerically. This is doing it graphically. And believe it or not, that's what the function does look like. There's a hole in it at x equals 0, but that hole is at the value y is equal to 0. Okay? So that's how you get it graphically. Analytically, that's the way to go. Okay, I think anyway. All right. Now, we did example 1. The book skips example 2, so that's where we'll pick up next time. And let's see if we get far enough to do any homework exercises. Let's try to. Let's do some of the odds 5 through 9. They're all found at calcchat.com. They want you to do the table. If you can figure out a way to do it without the table, fantastic. Okay, but you can do it with the table. Any of those odds. They're all at CalcChat. Number 5 is also at CalcView, so you can go there. And you can also do any of the odds 11 through 19. They want you to set up a table like we did before, like they show in 5 through 9. You don't have to. If you can think of a way to make that work without it, try it. See what you can find. Okay? If not, you can always do the table. All right. They're all at CalcChat, and none of those are at CalcView. We'll stop there and pick up the rest of those next time. Any questions? All right. Good deal. We will see you next week, I guess it is. Yeah, it's already Wednesday. So, have a good weekend.
Yeah, we don't see each other Monday, do we?
Oh, yeah, you see each other. I'm not going to be here. Okay, I meant to tell you that. Good point. Okay. So we only have another one-day work week next week, huh? Some people just like these things, don't they?
Oh, yeah, it's a great start. Huh?
Yeah.
Hey, do I get the decount for my parking?
Yeah, at the cashier's window. Huh?
The cashier's
The cashier's window. Just tell me you can do it. Yeah. I did worry a little bit last term because I thought, oh, he's found that big money and he's out of here. And then I thought, oh no, he was kickboxing and got all banged up and he's injured.
Yeah, I told my ACL.
You did?
Yeah.
Okay. Are you going to quit that garbage? You're going back to it? Yeah, I was afraid of that.
I just got to heal up.
Okay.
I can take a picture.
Of what? You want the ISBN?
Yes, sir.
I'll see you
Okay.
next Wednesday.
All right. Take care. We'll see you Wednesday.
And I can take a picture of the work.
That's right.
5 through 9 and 11 through 19. 5 through 9 and 11 through 19. I can take a picture of it. 5 through 9 and 11 through 19.
Oh, yeah. And, do you want actually a picture of those homeworks?
Yes, sir.
Okay. You want just the second part or you want the first part too?
I'll get both of them.
Okay. Okay. That's one page is that one.
Thank you, sir.
And you can go to CalcChat without the book.
Yes, sir.
Okay. And then the ones I just assigned were 5 through 9 and 11 through 19, so that page covers it all. Yes, oh, look at this. Excellent. Excellent. Thank you. Got it. Uh-huh.
Yes, sir. Do they got the books at the Birmingham campus?
I don't know. Do they not have it here?
I went in here.
Okay. I talked with him on the phone Monday evening, and he indicated he was going to order it. So I would go back down here and see if he's ordered any for here. Because, I don't think they'll have it there because Miss Martin decided to use the old edition, not this one.
Yes, sir.
But if you're on that campus, go and check. But,
I'm going to tomorrow. If they don't have it, I'm going to tomorrow.
okay. Okay, yeah. Good deal. All righty.